about multiplication and division as it relates to rational numbers. And the first thing I'd like to take a look at is the definition of multiplication. The definition of multiplication says if we have two fractions, a over b and c over d, then we would multiply the numerators together, a times c, and we would write that as a new numerator divided by the denominators multiplied, b times d, and that is our new denominator. First thing I want to show you is a rectangular region that illustrates how this works. So the first thing we're going to do is we're going to create a rectangle. And our rectangle, we're going to be multiplying the fraction 3 over 5 times the fraction 3 over 4. So the first thing I want to do is I want to take my rectangle and I want to divide it into 5 equal columns. And I will do my best to make them look equal. And then I'm supposed to shade 3/5 of this diagram. So that means 3 of these 5 columns. So there's 1, there's 2, and there's 3. The next thing I'm going to do is I'm going to take the entire diagram and I'm going to divide it into 4 equal pieces. Now dividing it into 4 equal pieces means that I actually, in order to not confuse it with the diagram as it's currently drawn, I'm going to draw those 4 pieces. I'm going to draw them horizontally instead. So there's dividing the whole big rectangle into half. We're going to half each of those halves. And lo and behold, if I only consider the horizontal lines, I have 4 rows. So here's row 1, row 2, row 3, and row 4. And of my 4 rows, I'm supposed to shade in 3 of them. So at this point, I actually am just going to concentrate on the part of the diagram that's shaded. So if I ignore the rest of it, I want to shade in 3 rows of these 4. So here's row 1, here's row 2, and here's row 3. And I have now shaded in 3/4 of the shaded red 3/5 picture. And if you count the boxes that are double shaded in the red and the green, I have 9 boxes that are shaded in. And if you count the entire number of boxes from the whole rectangle, I have 20 boxes. And if you take a look at the original fractions, 3 times 3 is 9, and 5 times 4 is in fact 20, verifying that same fraction to us. All right, we're going to take a look at some of the different properties of multiplication. The first one we're going to talk about is identity and inverse property. So an identity is the number 1 for multiplication. It's the only number we can multiply a value by and not change it. And the inverse is the value that we would multiply by to get back a result of the number 1. So if we have a fraction a over b, then the inverse, or multiplicative inverse, is b over a, because a over b times b over a equals 1. We also have the distributive property for multiplication over addition, is what that should say, not division. Multiplication over addition. It also works the same way over subtraction. And what you see here is you see a fraction that is supposed to be multiplied across those parentheses. And that's exactly what you see. You have a over b times c over d, and then you have a over b times e over f. The multiplication property of equality simply says that if I have 2 values that are equal, and I can have a third value, e over f, any rational number, I can multiply each of my 2 original numbers by the number e over f, and they will also still be equal. Inequality is very similar. It says that if I have an inequality, a over b is greater than c over d, and I multiply by a positive number, that the inequality stays the same. And then it says if I have an inequality and I multiply by a negative number, that the direction of the inequality switches from greater than, in this case, to less than. Multiplication property of 0 simply says that if I multiply by 0, I get 0. All right, so what we want to do is we want to take these properties and we're going to see how they're used to solve equations. So the first equation I have here is 3/4 x equals 1/5. So my goal is to get this to say x equals some value. So the first thing I'm going to do is I'm going to multiply by the multiplicative inverse. So for the value 3/4, the multiplicative inverse, that is the reciprocal, is the value 4/3. So we've got 4/3 on both sides. I'm allowed to multiply both sides by 4/3 because that is the multiplicative property of equality. On the left-hand side, when I multiply 3/4 and 4/3, I get the number 1. The number 1 arriving from this is the multiplicative inverse property. On the right-hand side, I multiply across the top and I get 4, across the bottom and I get 15, and that is the definition of multiplication. Okay, one more time. On the left-hand side, I have 1 times x, and that's actually equal to the value x. And that is happening by the multiplicative identity property. And I end up with that equaling 4/15 on the right. Now we're going to do one that's a little bit more complicated. It's more complicated because it doesn't just have multiplication involved. It also has some addition and subtraction involved. So the goal is to get all of the terms that have x on one side and all of the terms that do not have x on the other side. And the way I'm going to do that is I'm first going to move this 1/4 by subtracting 1/4 from both sides. Now I can do that by the additive property of equality, and that we learned about in section 6.2. I'm going to kind of do two things at once. I'm going to go ahead also and move the x over 6. Again, that's another property of the additive property of equality. And so I can do minus x over 6. So just rewriting this a little bit more cleanly. Well, let me first identify that this right here is going to become 0, and this is going to become 0. Oops, I made a mistake there. The one marked out correctly. This one's going to become 0. That's happening because of the additive identity and inverses property. Let's write that a little bit better. All right, so I'm just going to rewrite the pieces that I have. This is now says 2x over 3 minus x over 6 equals negative 1/2 minus 1/4. And in order to combine these, I need to have common denominators. So looking at the first one, I will multiply it by 2 over 2 to make the first denominator 6, just like the second one. That will give me 4x minus x over 6. On the right-hand side, again, I will multiply the first fraction by 2 over 2. That will give me negative 2 minus 1 over 4. So if I simplify this, I get 3x minus 6 equals negative 3 over 4. And all of this is from the definition of multiplication and simplifying. All right, so on the left-hand side, I end up having a fraction that reduces. This 3 and this 6 can both be divided by 3. So I have x over 2 equals negative 3/4. And then my goal is, again, to get x alone. So I will multiply by, this is the same as having 1/2 on the left. So I will multiply by the multiplicative inverse of 1/2, which is the number 2. This is the multiplicative property of equality. And then this 2 and this 2 here, those are going to simplify right to the number 1. So I've got 1x, and that's the multiplicative inverse property. On the right-hand side, I end up getting negative 6 over 4. This 1x becomes x, that's the multiplicative identity property. And on the right-hand side, I end up with negative 3/2 by simplifying. then a division. Division of rational numbers says the following. We have A divided by B, A over B divided by C over D, and it's equal to some other rational number. That only works if that rational number could have been multiplied by C over D to get back A over B. And this is the way that students are first introduced to division when they do whole numbers as well. For instance, if you're trying to figure out how to divide by 2, if you want 6 divided by 2, often you will ask a student, what times 2 equals 6? And they would say 3. So 3 times 2 equals 6. So you define division in terms of that multiplication. Now, the algorithm for how we actually process that is that if we have 2 fractions and we are dividing them, such as A over B divided by C over D, we can turn that into a multiplication problem by taking the second fraction, and it must be the second fraction, and using its reciprocal. What I'd like to show you is why that works. So we're going to consider writing this A over B divided by C over D. But I want to write it as a double fraction, or sometimes we will call it called a complex fraction. Doesn't look especially pretty, but it is the same meaning. Now, if I have a complex fraction, or any fraction actually, I'm allowed to multiply the numerator and the denominator by the same value. So I actually want to multiply by the value D over C. Clearly, I want to multiply by D over C because it is the reciprocal of C over D. So this denominator actually ends up being the number 1. So I end up in the numerator with A over B times D over C divided by 1. And division by 1 yields the same result that you originally have. So we have A over B times D over C, which is exactly what we said we could do. All right, so I want to show you by picture form what it looks like to divide with whole numbers so that we can talk about what it looks like to divide by a fraction, because that idea is sometimes very odd to say I'm going to divide by a fraction if you don't have the right description or definition in your mind of what it looks like to divide by a whole number. So we're going to take a look at this form. Just a moment here. All right, so we have a circle, and I want to clone it. I want to turn it into an infinite cloner, and we will create 6 of these because we want 6 that we're going to divide. There's 4 of them, 5. And now I have 6. So one way to talk about division, in particular if we talked about dividing by 2, is that we could put these into 2 separate groups. So we have 6, and I take 6 people and I make 2 groups with them. The other way that we can talk about division is we can talk about division as though we're creating groups of size 2, kind of like when I put you in pairs or groups in class. I want to do groups of size 2. So if I do groups of size 2, I circle pairs, and I end up with 3 groups of size 2. And I like that because that lends itself very well to talking about 6 divided by 1/2. So again, I'm going to create 6 of these guys. There's 2, 3, 4, 5, and 6. And I want to create groups of size 1/2. So obviously I can't be talking at this point now about people, but I can certainly be talking about cookies. So if I had 6 cookies and I want to create cookies of size 1/2, I would simply divide each cookie, of course, in half. And if you take a look, then I have 12. I know it sounds funny to call them this, but I used the word before. So 12 groups of size 1/2, or 12 halves, not 12, excuse me. Yeah, 12, I said that right. 12 groups of size 1/2. So I have 12 of these different halves of cookies. Right, last thing in this section that's of interest to us is to talk about exponents. And the reason we're talking about exponents is because exponents are just a condensed way of using multiplication, repeated multiplication anyway. So the first thing I want to do is to talk about the properties and remind you of the properties of exponents, and then I'm going to show you why those properties actually work. So the first property is a to the m times a to the n. And before I get started, let me remind you what this notation means. If you have a to the n, it means that you're multiplying a by itself n times. So a to the m times a to the n, the property is that we add those exponents. Now property 2, if we divide them, that actually says that we would subtract the exponents. If you have an exponent raised to another exponent, that is multiplication of your exponents. If you have two terms that are multiplied, and it is important that they're multiplied, if they're added or subtracted, properties 4 and 5, they don't work. This is specifically for multiplication or division. When you multiply two values together and you raise them to a power, you can actually do what sort of looks like distribution of that power. So ab to the m is the same as a to the m, b to the m. Likewise, a over b to the m is a to the m over b to the m. Now number 6 is a little different. Number 6 actually has a negative exponent. Negative exponent actually turns your fraction upside down. So a over b becomes b over a. And the negative m becomes a positive m. And then of course it could be applied rule number 5, and we could distribute that m over those. Now what I want to do is I actually want to show you why in the world these properties work. Okay? We're going to do them in most cases with some concrete examples. So the first one is a to the m times a to the n, and I told you anyway that that should be the same as adding the exponents together. So we're going to give it a try, and we're going to see if that works. So a to the third, by definition, means a times a times a. And then a to the fourth means a times a times a times a. There's 4 of them. So a condensed way of writing this would be a to the 7th. And why is it 7? Because 3 plus 4 is 7. Okay, so property number 2, that actually says that we should subtract the exponents. So m minus n. So we're going to give that a try. A to the 4th again means a times a times a times a, 4 of them. And then a cubed is 3 of them. And then one of the things that you learn is that you're able to reduce these if you divide them both by a power or by a coefficient of a. So this would actually end up giving us just single old a when we're done, namely a to the 1st. And why is it first? Well, because 4 minus 3 is 1. That's the second property. The third one says that if I have a power raised to a power, like this one, I would multiply the powers together. So I'm going to take a look at what it looks like to have a cubed squared. Well, a cubed squared, well, squared means I have a cubed times a cubed. And literally, without using any other properties, a cubed means a, and another a, which is a grand total of a to the 6th. And again, why is it 6? Because 3 times 2 is 6. All right, so taking a look at the next one, ab to the m, I said that this was a property that sort of looked like a distribution of exponents. Works for multiplication and division, not for addition or subtraction. But here's what it means. I have ab to the 4th. Well, this is ab times ab times ab times AB, and because multiplication is commutative and associative, which means I can reorganize it, I can rearrange it, I have 4 A's here, and I have 4 B's here. So it's A to the 4th, B to the 4th, because the original one was AB to the 4th. Number 5, I have A over B, and it's raised to the m. That's the same as distributing the m to each of the numerator and denominator, respectively. By a similar argument as the last one, I can take a over b, and I can multiply it 4 times, because it says a over b to the 4th. And if I do a quick count of this, I have, straight across the top with the definition of multiplication, I have a to the 4th. Straight across the bottom, I have 4b, so that's b to the fourth. And why is it a to the fourth over b to the fourth? Because the original one was a over b to the fourth. And my last property down here says I have b over a to the m. And I want to show you this one. This one's a little bit more unusual because it has the negative exponent. It's not like any of the other properties for that regard. And so if we're taking a look at a over b to the negative fourth, we end up having, well, we sort of want to think about it by breaking apart what negative 4 is. Well, negative 4 is a negative 1 times fourth power. Negative 1 is actually a notation for reciprocal. So if we have a negative 1, it means take the reciprocal. This is b over a. And then this is raised to the fourth power. So a over b to the negative fourth becomes b over a to the fourth. All right, now there's actually a couple more that I haven't mentioned. There's some additional properties that are good to know. One of them is this famous a to the 0 equals 1. And sometimes people sort of think of this as it's a definition. It's that way because we defined it to be that way. And I want to argue that that's not really a very good way of thinking about this. It's very provable with the other facts we've used. So I'm going to actually use those other facts. So the first thing I want to recognize is that a to the 0 can actually be obtained by taking a and subtracting two like values. So if I have a to the m, I would do m minus m, and of course it gets 0, so it's the same as a to the 0. But if I again use my properties in reverse, I can write this as a to the m over a to the m. That's property number 2, used sort of backwards. And then of course, anytime we divide a value by itself, it's the number 1. So if you look at where we started, a to the 0, and look where we ended, it equals 1, then a to the 0 in fact does equal 1. Last one, property number 8, a to the negative m. This is the same as 1 over a to the m power. So this is kind of like property 6. I can take this negative 3 and I can write it as negative 1 and 3, because negative 3 is negative 1 times 3. We already talked about negative 1 is a reciprocal, and the reciprocal of a is 1 over a, and then a power of 3. And of course, according to rule number, or property number 4, I think it is, we can distribute that cubed to each of my terms. And finally, we recognize, of course, that 1 cubed is 1. So this becomes 1 over a cubed, which came from a to the negative 3. All right, so I think we have time for just maybe just example 6. So let's take a look at example 6. We're going to write in simplest form with positive exponents. What I want you to understand is that there's more than one way to do this problem. As we're taking a look at this, if you think of another option and you're carefully working through it, that's okay. Again, there is more than one way. So I'm going to use the properties in as much as possible exactly like they are. So property number 2 says that if I have an a on top and an a on bottom, then I can subtract the exponents. So my exponent on top is 1 minus my exponent on bottom, which is negative 3. Now I can do the same thing with b. b has an exponent on top of 4, and I can subtract the exponent that is on b on the bottom, which is 2. If I simplify this, minus a negative here becomes addition. So 1 minus negative 3 is actually a to the 4th. And then b to the 4 minus 2 would be b squared. And that is simplified form with positive exponents. B is a little different because on part B, I actually have numerical values instead of a variable a or b. So actually, in order to combine the 2/5 and the 4/25, I need to be able to have them be identical. Now, as you're taking a look at this, 2 over 5, 4 over 25, hopefully you're looking at and saying, those seem familiar. In fact, if you take a look at 4, it is 2 times 2. And 25 is 5 times 5. Or another way of writing that is that I could write this as 2 over 5, and they're each squared, because 2 squared is 4, and 5 squared is 25. And this is to the negative 6th power. Again, there's lots of ways to do this, and I'm going to show you just one of them. So I'm going to use one of our properties in reverse. The property that I'm going to use is that I'm going to use the property that says powers raised to powers. And so this power of 2 raised on the 2/5. In fact, let me do it in 2 steps. I'll write this 2/5 here to the 3rd. I'm going to write this 2/5 as 2/5, all of it squared, and all of that is then raised to the -6. I like it written that way. The reason I do is because I end up having, up here, I end up having, well, let me rewrite the first part, 2/5 cubed. Then I can actually combine these two with multiplication. And that is property number 4, I believe. So I can write again 2/5. And then I have -12. So these have the same base now, 2/5, different exponents, and that brings me back to property number 1, which says I can add my exponents together. So I have 3 plus -12, and 3 plus -12 is, of course, -9. And I'm actually all done, that is simplest form, but I don't have the positive exponents part, so I need to do one more step. That one more step actually uses property number 6. Property number 6 says if I have a negative exponent, I can flip my fraction upside down, so 5/2, and I can write that exponent then with a positive. So you can either leave it written like this, or if you'd like to, you can leave it written as 5⁹/2⁹. Both expressions would be correct. And we'll stop there for today.